Hi, welcome back. In the last few videos, we have understood what is a reflexive relation, what is a transitive, and what is a symmetric. And we have also defined equivalence relationship. And we did see a few examples, understanding a reflexive, symmetric, and a transitive relation. Now I'm going to pick up an example or a question from the exercise 1.1 of the NCERT textbook. Okay, now that is my question that I'm going to be trying and solving it for you. So I have the set A, which has been defined to me here as 1, 2, 3, goes on till 14, and the relationship R is been defined to be as x, y, such that 3x minus y is equal to 0. Let's take this relationship. It says 3x minus y is equal to 0, which otherwise can be written as y is equal to 3x. It simply means that if I'm picking up an ordered pair, x, y, the second element is supposed to be 3 times the first element. Okay, so we do have an understanding of what is A cross A. I'm not going to write that. Please keep that in your mind. Okay, for reflexivity. It is very easy to prove that this particular relation is not reflexive because 1, 1 will not belong to R. It simply means that the second element, which is 1 itself, is not 3 times the first element, which is again 1. What do I mean? 1 is not equal to, or the second element, if I'm saying 1, 1, it is the second element, which is not equal to 3 times of the first element, and hence this relationship cannot be reflexive. So how do we write this? Very easy. 1 belongs to A, but 1, 1 does not belong to R. Hence R is not reflexive. Now let's check for symmetry. Do you think this particular set is symmetric? Let's see. Okay, again I'm going to give an example and prove that it's not symmetric. 3, 1 belongs to 3, 9, I'm sorry, belongs to this particular set, isn't it? Because the second element 3, 9 belongs to R. You see, the second element is 3 times the first element. However, but 9, 3 does not belong to R. Therefore, R is not symmetric. Okay, now let's look for transitivity. I think it's not even transitive, but I'm going to check that for you. For transitive, again I'm going to give an example and prove it's not transitive. 1, 3 belongs to R, isn't it? Because the second element is 3 times the first element, and we just saw that 3, 9 belongs to R, and 3, 9 belongs to R. But does 1, 9 belong to R? No, it does not, because the second element is not 3 times of the first element, and hence R is not transitive. Alright, that's very simple to prove. See, let me tell you something here. If you have to prove somebody to be a good person, it's a bit difficult task. You might say, no, it's not. I just believe the person and I'm going to say he's good. In reality, that's not true, because a good person for you is your perspective, isn't it? Do you know every aspect about this person, right? From the birth till you know him now. Well, until now he might be good, but tomorrow if he does something and he's on television, then you have an issue, isn't it? So identifying a person or giving a verdict that a particular person is good is very, very difficult. But given a chance to prove a person is bad, it's very easy. You can just pick up any example or any incident that has happened. You can tell others that this guy did this on that day on this particular situation, and that is exactly why this is not a good person. Getting me? So proving someone to be bad is very easy. You can just give an example of some situation. But no matter how many good things a particular person has done, you would always be a bit more hesitant to prove that or accept that this particular person is a good person, right? So you check everything about him, only then you go ahead and prove him to be a good person. That's exactly how this works. You look at this. I just gave an example and proved that this is not reflexive. not symmetric, and not transitive, isn't it? Because I already knew that this is not symmetric, reflexive, and transitive. Okay, so if it is, then you will have to generalize and write it. How will you do that? We will learn the methods of proving these things in the few more videos coming up. Okay, I'll be doing one more question today in this video, and then we will look at more questions in the next video. Okay. Alright, now let's go back and look at the next question. That's the next question that we have. The relation R is on a set n of natural numbers. So here the relation is being defined on n cross n. So ideally we know that n is an infinite set. Again, this is an infinite set. So n cross n is going to have infinite number of ordered pairs, which we cannot pick. Alright, however, if you look at this relationship here, the restriction is being applied, which means the domain of the relationship is less than 4. To understand what's the domain and codomain, please go back and visit my videos. So, this being the set of natural numbers, 1, 2, 3, 4, 5, it goes on till infinity. Again, I have another set natural numbers, 1, 2, 3, 4, 5. I think I'll have to increase this here. I'm just going to increase this. Okay, so let's pick up another set here. 5, 6, 7, 8, 9, and goes on. Okay, now what is he saying here? He's saying that the second element is 5 times more than this first element. So 1 will be connected to 6, 2 will be connected to 7, 3 will be connected to 8, 4 will be connected to 9, and there will be another element which is 10. So 5 will be connected to 10. Is that true? No, that's not true, because I'm supposed to be restricting myself to less than 4, and hence this connection is not going to happen. This cannot happen because my domain has been restricted. Okay. It's a difficult task to actually correct myself on this particular video, right? Okay, but I think I did a good job. Great. Now, so what are the order pairs belonging to this? Again, in this particular relationship, I'm able to write the order pairs, which means that I can prove it in a very simple fashion. 1, 6, 2, 7, and 3, 8. These are the order pairs belonging to the relationship R. Okay, is it reflexive? No. Is it symmetric? No. Is it transitive? Well, we will come to that. For reflexivity, alright, 1 belongs to R. Oh, sorry, 1 belongs to N, isn't it? 1 belongs to N. However, but 1, 1 does not belong to R. Therefore, R is not reflexive. Okay, let's look at the next one, symmetric. For symmetry. For symmetry. Now what do I have here? I do see that 1, 6 belongs to R. However, 6, 1 does not belong to R. 1, 6 belongs to R, but 6, 1 does not belong to R. Therefore, R is not symmetric. For transitivity. Okay, now when I'm checking transitivity, I have to put in the condition that the first two set or the first two order pairs belongs to the particular relationship R, which is A, B belongs to R, B, C should belong to R. Keeping these two conditions in my mind, I have to then go ahead and prove that A, C belongs to R. Well, that's the thing about transitivity. For symmetry also, I have to have that condition that A, B belongs to R. That should be true. Only then I can go ahead and find out if B, A is belonging to R. Great. Now when I come back to this particular set, I'm unable to find out a third element, because I do see 1, 6. Is 6 related to anything? No. Here also 2, 7, but 7 is related to nothing. 3, 8. 8 is related to nothing. Ideally, I'm unable to prove that this particular relationship is not transitive. Because I'm unable to prove that this is not transitive, this particular relation will now be a transitive relation. It is something like this, if you're in a court and if you have to, catch hold of a thief, the thief is going to be innocent until he is proven guilty, isn't it? No matter what he has done, he has to be proved to be a guilty person. Until then, he is considered to be an innocent. That's exactly what this is, You cannot prove that it is not transitive, and hence, it is transitive. Cannot contradict transitivity. Therefore, or hence, R is transitive. Okay, so that's my transitivity. So this particular relationship R is not reflexive, it's not symmetric, and nor is it transitive. I'm sorry, it is transitive because I'm unable to prove that the relationship is not transitive. Now let's look at the third question. This is an interesting question. Let's see how to prove this. Okay, so the relationship has been defined on Z cross Z. The first set is also Z and the second set is also Z. Now what is it saying? That the subtraction of two integers should be an integer. That is what it's saying. If it is, then pick that up. Okay, well, this is reflexive because you take any integer, subtract it from itself, it's going to get you a 0. And 0 is an integer, isn't it? So 1, 1, 2, 2, basically any x, x belongs to R, and hence R is reflexive. For reflexivity, I'm taking some random number, some arbitrary number. Now this is what I was talking about, if it is true, I'll have to generalize and write it. If it is not true, I can just pick up an example and prove it. Now I'm generalizing it. A belongs to Z. Now what is A minus A? 0. And 0 belongs to Z. What does that imply? That implies that A, A belongs to R. Because I've just gone ahead and proved that 0 belongs to Z, which is an integer. Therefore, R is reflexive. Okay, great. Now let's try and prove if it is, try and check if it is symmetric. For symmetry, okay, what do we do for symmetry? First of all, I need to have the first condition to be true. Based upon that, I'll check if the second condition is true. Okay, I know it is symmetry, so I'll have to generalize it. Once I prove it, you will also realize that yes, it is symmetric. Let's see how. Let A, B belong to Z. I'm taking two elements belonging to the integers. What is A minus B? I'm again going to say let A minus B be equal to C, which is belonging to the integer Z itself. What is C? It's the difference between them. So basically what am I saying here? I'm saying A, B actually belongs to R. This is the condition that I was talking about. For symmetry, we have to put this condition. Now, taking this condition to be true, I will go ahead and prove that the other condition will also be true. Okay, I have here told that A minus B is equal to C, right? I'm now going to write it as this. B minus A is equal to minus C, isn't it? If 2 belongs to integers, then certainly minus 2 also belongs to integers. So that's what this means. So this also belongs to integer. So A minus B and B minus A both belong to integer, which means B, A belongs to R, isn't it? So I've gone ahead and now proved that A, B belongs to R, keeping that condition to be true. B, A also belongs to R. That is also true. Therefore, R is symmetric. You see that? I had to generalize it. Now I'm going to try and prove the transitivity. If you're following me, you should already know that this relationship or this relation is actually transitive. Okay, for transitivity, we have to pick 3 elements. Let A, B, C belong to R. And I have to take the first 2 conditions let A comma B belong to R and B comma C belongs to R. I'm taking these two conditions to be true and then going ahead and proving that the third condition is also true, which is A comma C belongs to R. If these two conditions are true, I simply mean that A minus B is an integer. Why don't we actually take that as some other element? That will be helpful for us, which is equal to D. Let's say D belongs to Z and B minus C, let's say that's equal to E, belongs to Z. Okay. Now what I'm going to do is I'm going to add these two, this and this, the left hand sides. A minus B plus B minus C is equal to D plus E. This and this gets cancelled, so I'll have A minus C is equal to D plus E. We know that sum of two integers is always an integer, isn't it? Therefore A minus C belongs to Z, whatever we get after subtracting. Okay, I'll have to manage that here. Alright, so what have I done here? I've gone ahead and proved that A comma C belongs to R. Therefore, R is transitive. So what kind of a relationship is R? Any guesses? Yes, it's an equivalence relation. Let's go back and check this. It is reflexive, it is symmetric, and it is transitive. If you actually give it a thought, you will also realize that this is a relation, because when I'm actually checking this, you take any integer, you subtract it from another integer, you will always end up with an integer. So this relationship R will have the entire Z cross Z, which means it's a universal relation. And whenever it's a universal relation, by default we should understand that it is equivalence, and we need to modify our proof in the similar fashion. Okay, that's it for this video. Thank you for watching.